Yes, good afternoon. This is Thorsten Cruz, Cruise Analysis and Cruise Training. Today, I would like to discuss a little bit the training opportunities in the field of part design, mold design, and processing. Over many, many years, we have now noticed that it is important to strengthen our engineering capabilities by adding skills that will benefit our companies. In the injection molding industry, however, it is very important to get trained on a variety of capabilities. We all know that the injection molding industry, we have to know part design, we have to know mold design, we have to know the molding process, and of course, we also need to know a little bit more about molding. Injection molding simulation, as you know, is one tool for our engineers to make this process of injection molding visible. Within the Moldex simulation tool, we can visualize polymer material flow, we can evaluate part designs, we can evaluate mold designs, and we can try to optimize the process. So a simulation tool like Moldex can visualize the molding process. For the last 25 years, I've done simulations and gained so much insight and knowledge in the process of injection molding that it was time to bring this expertise to a different level, meaning bringing this to engineers all around the world. And that's why we started Cruise Training. So the Industry 4.0 meets Training 4.0. What the mantra here is that we need to have a more industry-wide training tool that looks at cause and effect behaviors in injection molding. And one tool is the e-learning. E-learning, as we know, is a standard nowadays. It's not the future, it's the present. We all know that you can get learning done through online universities. Yeah, it is not for the young, as you might think. No, it's for everyone. Yeah, e-learning is important nowadays. Some people say it's not accepted. Well, actually, it's expected of the industry to have an e-learning platform to help our industry grow its knowledge. The e-learning market itself will be growing steadily. We, as you know, we can learn anything nowadays through the internet. We can use YouTube, we can have, as I mentioned, online universities. And in our field of injection molding, however, there are just a few companies that provide online training. Our big important aspect in learning is the cause and effect. And you will hear me say this again and again, that learning the cause and effect behaviors in injection molding is the most important aspect you have to learn, because it is not only necessary to know how to design a part, it is important to understand the impact between the polymer material and the part design. Only then you really can optimize a part design. And only then, when the part design is optimized, you should go in and optimize the mold design. And only then you can optimize the process. So it is a very interactive behavior. And as more complex a part design gets, as more complex these behaviors will get, So we have developed a program which we call the Circle of Knowledge. And the goal for the Circle of Knowledge is to basically build synergistic teams. I would like the part designer to know more about the polymer material. I would like the mold designer to understand more about part design. And at the end, the process technician that has to make it work on the actual molding machine usually gets a mold and has to make it work. But the process engineer needs to also understand part design and mold design. And the reason is, if the process engineer understands, for example, how a mold cooling system is routed, he or she can take this knowledge and improve on the process. So our system, we believe, is important. That means understanding the cause and effect behavior. That's the reason why we developed the Circle of Knowledge program. It is for part designers, mold designers, and processors. It is online training available 24 hours a day, 7 days a week. And we have very concise 15 to 20 minutes long lessons to teach subject matter based on cause and effect behavior. The system uses multi-3D technology, technical animation, graphics, explainer videos. We will actually use Moldex simulation to show cause and effect. So training Industry 4.0, the buzzword we hear everywhere, meets training 4.0. In my vision, every engineer can have this program on their tablets, either to design parts or actually take this information and go to the molding floor and actually review lessons on the molding floor if there is a need to explore an opportunity in processing. Okay. Currently, we have 61 lessons. The next 9 lessons will be available within the next probably 2 months. We have lessons on all different subject matters. These are what we call micro-learning lessons, short, concise, focused on a single topic. They can be, again, accessed in order or as needed. We have foundation levels. We have lessons on polymer materials, on specific part design issues, on mold design issues, on processing. In the future, we will also develop a lot more lessons on molding defects, etc. So this is a training tool that is supposed to be used by anybody in the injection molding industry. We will add 20 or 24 new lessons every year. Sorry, every day would be nice. So every individual has a training opportunity. Yeah, you can again use the system 24/7. We have a learning management system behind it, so you can account for your progress. We have quizzes, and with all that, you can potentially use this to advance your career on an individual person basis. Or you can develop a training tool for your company. We have customers that use our training tool to set up an in-house training. The training supervisor will then use our material to go through these lessons with their engineers on a potentially weekly basis or bi-weekly basis. Some of them use it at the lunch and meet at the company to go over a lesson to learn while they meet at lunch. Yeah, so this system is very, very flexible. Again, it can be used anytime, anywhere for an individual or as a team. Some companies have a seat for the engineering team, for the process team, for the sales team, to just learn the cause and effect behavior in injection molding. We'll have a certificate base. So when our first 70 lessons are done, we will close level 1 and we have a certificate available. What that means is people can go through all of our lessons. They can go through the quiz. If you pass 80% correct answers, you can get certified by cruise training as well.
Tape point gates can have positive or reverse taper design. A positive taper has the smallest diameter at the intersection of the part, while the reverse taper design has the smallest diameter at the intersection of the main pin gate runner segment.
As you can tell, we use lots of animations, real voiceovers to really make this a very interesting multimedia experience when learning. We use a lot of graphics, animations that we are producing. We also use, of course, Moldex3D. We actually create lessons using Moldex3D to show the cause and effect behavior. We will show things that are wrong from a simulation perspective and then show what is right to make the engineer learn the cause and effect behavior. The site will be and is multi-language. At the moment, everything is in English, of course. We have our first 15 lessons in Mandarin available as we speak. Spanish and Portuguese lessons will come in the future. Again, the certification program is there. Our whole goal is to develop training for many different levels. At the moment, we have level 1, but we will adding lessons for level 2, 3, and 4 in the future, and of course a master lesson. Every time we go up in a level, the complexity will get higher. We use more complex part designs and mold designs to show cause and effect behaviors. Every lesson will have an introduction. Every lesson will have objectives. Every lesson will have the main body of understanding what we're trying to teach. Every lesson will have, in general, simulation examples. Every lesson will have a review, conclusions, and a quiz. When looking ahead, our goal again is to develop 20 to 24 new lessons every year to add to our system that eventually will have hundreds of lessons available on this knowledge and training side. We call this a knowledge system and a training tool. And why are we calling this a knowledge system? Some companies, we found out, they really use this as a knowledge system, almost like a Wikipedia for molding. And other companies use this as a true training tool where they have a training supervisor that is administrating the engineers and check their progress by reviewing their quiz scores, and then go back and help the engineer along in understanding the cause and effect behavior. So what's next in the future? We will add more lessons for molding defects like short shots, voids, sinks, gate blush, tiger stripes, warpage. We will have special processes lessons. Those lessons are for example, LSR molding, powder injection molding, mucil, gas assist, water assist, insert molding, over molding, two-shot molding. For all of these special processes, eventually we will have lessons available for you to study the cause and effect behavior. Here's just a small glimpse of what we currently have and what we are working on. We have a list of future lessons that are hundreds of lessons long. We also can develop customized training. Some companies have approached us and say, well, we do this, but we would like to have a training specifically for one subject matter for our specific company molding project. And we can do that too. And again, our goal is to develop hundreds of lessons for all subject matters related to injection molding. And let me show you now a main lesson. The lesson for today was about voids and bosses. So let's look at an actual training lesson on the voids. Here's our system, just so you can see it. We have all our lessons listed, again up to 61 at this time. And for today, we have a lesson on bosses. We'll go in and play this lesson, and after the lesson is done, we can have some more discussions and details.
Bosses are included in part designs for various purposes, from a solid pin used as a locating feature to a screw-mounting feature. As with other part design features, bosses can influence the moldability, function, appearance, and quality of a part, and should be analyzed and evaluated for optimal results. In this lesson, you will learn how to evaluate various boss designs to determine an optimal design strategy. What risks are involved with incorporating boss designs into molded parts? How to evaluate boss design impact on filling behavior, cooling temperature, volumetric shrinkages, and sink marks. There are numerous industry guidelines on boss designs. Let's look at a few examples to evaluate the aspects that work and those that could create issues. This image, for example, shows a boss design with a core pin that is too short. This will create a thick section, causing longer cooling times, higher shrinkages, sink marks, and possible voids. The inside of a boss is formed by a core pin in the mold. The taller the boss, the hotter the core pin will become over time, especially near the top. Because of this, plastic at the bottom of the boss hole remains hotter longer, resulting in shrinkages, sink marks, and voids. Also, the strength and stiffness of the assembly boss is potentially compromised. Here is a boss design with a core pin that is too long, creating a thin section. In this case, filling hesitations may occur while the thin section fills, which could result in a short shot or pinhole entrapment. More information on this topic is available in Lesson 9, Gussets. Another boss design option shows that the core pin length was optimized, and in addition, a generous radius was added. As in the first example, this would create a thicker section that could lead to longer cooling times, higher shrinkages, sink marks, and possible voids. The boss design here indicates that the core pin length was optimized, but this time an appropriate radius was added. This would normalize the cross-section thickness and slightly increase the wall thickness. Lastly, this boss design features a reduction in the nominal wall thickness and a negative radius. This design would reduce wall thickness in the cross-section area and could be an option for minimizing shrinkages, sink marks, and voids. Keep in mind, however, that by reducing wall thickness, a part will have less stiffness and strength. Successful boss design incorporates height, thickness, hole depth, and blend radius to avoid thicker thin sections, and thereby minimizing cooling times, shrinkages, sink marks, and voids. Thick wall sections around bosses lead to slow cooling behavior, higher shrinkages, higher molded-in thermal stresses, greater sink marks, increased voids potential, poor surface quality, lower material strength, premature part failure. Generally, bosses are designed as a screw assembly feature and have an outside diameter around 2.5 to 3 times the screw diameter. If gussets are incorporated into the design, the outside diameter can be reduced because they will help to stiffen the boss design feature. For this lesson, we will evaluate a sample box part with two different boss designs. For our purposes, we will refer to the first one as the bad design, which has bosses incorporated into the corners and sidewalls. The second design, or the good design, has bosses which are freestanding, away from the sidewall, and supported by connecting ribs or gussets. We will begin by evaluating the filling pattern for both designs. In the first example, you can see how the plastic flows along the path of least resistance, with the thick boss areas filling first, followed by the thin areas. For the good boss design, the fill pattern is more uniform throughout the bosses, most evident in the freestanding boss. Let's look at the cooling behavior for both boss designs by examining the temperature during the packing and cooling phases at time intervals of 2, 8, and 16 seconds, and at the end of packing at 25 seconds. Starting with the 2-second interval, here you can see the temperature distribution in a cross-section of the two designs. The nominal walls of both parts remain at a higher temperature, but the first image clearly indicates where the thicker sections kept their heat. The thinner boss cross-sections on both designs show a rapid heat loss. At the 8-second interval, you notice a more significant temperature difference between the two designs, but both parts are retaining heat in certain areas. The bad design shows areas that remain at high temperatures, and the good design still shows heat in the intersection rib areas where the bosses are connected to the sidewall. At 16 seconds into the packing and cooling phase, the differences become more significant. The temperature in the thicker section in the bad design remains high, while most of the nominal wall thickness for the good design is now at a relatively even temperature. At this interval, you can also see that substantial temperature differences inside some of the bosses on the bad design. These differences will cause significant thermal stress variations, which could lead to cracks and premature part failure. At 25 seconds, at the end of packing, the thick sections are still so hot the material continues to shrink and develop thermal stresses. The corner boss on the bad design shows the biggest temperature variation, which will result in molded-in stresses. Moving on to volumetric shrinkages, you can see a very high rate of 13% in the bad design and only 4.7% in the good design. Shrinkages are highest on both designs between the boss and the nominal wall of the part. Our final evaluation will compare the resulting sink marks on the outside surface of our two designs. To best illustrate the differences, the results are scaled to the same sink mark depth of 0.15 millimeters. You can see more red and yellow in the bad design, which indicates deeper sink marks in comparison to the good design. This concludes Lesson 8, Bosses. In this lesson you learned how to evaluate various boss designs to determine an optimal design strategy. What risks are involved with incorporating boss designs into molded parts? How to evaluate boss design impact on filling behavior, cooling temperature, volumetric shrinkages, and sink marks. Bosses are design features that serve an important function in molded part assemblies. As we saw in this lesson, boss thickness, location, height, hole depth, and blend radius are all factors in optimizing strength and quality. If bosses are designed to be freestanding and supported by connecting ribs or gussets, they can successfully impact the moldability, function, appearance, and quality of a part.
Yes, everybody, this was a quick overview about one of our lessons to show you how we operate in the space of training 4.0. Again, our goal is to have this available to any engineer to learn the cause and effect behavior in injection molding. Parts getting more complex these days, and it is important to start the part design early, to optimize it, so before a mold has ever been built, the mold then therefore has a greater chance to be optimized, and therefore the process being optimized. It is our belief that only with knowledge of how the interaction works between the polymer and the part, the mold and the process, only then you will be able to be successful, stay competitive, and strive on an everyday basis.